Let's look at horizontal and vertical circle. Now, the first question that you will have to ask is this: what is an horizontal circle? As you can see right here on this diagram, it has the tension that is towards the center, and it has the weight that is going down. In this circle, the weight does not interact with the tension because it is perpendicular to the tension. So in this circle, the weight is not, or is ignored, because the weight does not interact. And please note that this circle right here is called the horizontal circle. All right, and I'm saying that in a horizontal circle, the weight, which is Fg, does not interact with the tension, all right, or with the centripetal force, and it is perpendicular to the tension. All right, so with this said, we can find the net force in an horizontal circle. We can therefore say that the net force in this circle is equal to, is F. Net force is F equal to the tension or the force acting towards the center, which we call the Fc, which is the centripetal force, is equal to mv squared over r. So in this case, we ignore the weights. All right, this is the weight, which is mg. We ignore the weight because the weight does not interact with the tension. So the formula we use for this type of circle is mv squared over r. And please, you must also note that centripetal force is also regarded as a net force. I repeat that centripetal force is also regarded as the net force. So here is the concept of a horizontal circle. The next circle you are seeing right here on your right is called the vertical circle. Now, in a vertical circle, as you can see on your screen, we have at least 4 points right here. We have a point right here. We have a next point right here. We have the top, and we have the bottom. As you can see right here, you can see that at the top, you have the tension and the weight going in the same direction. And you have at the bottom, you have the tension and the weight going in opposite direction. In this case, you can see that the weight is having an effect on the tension, one, and also the weight is interacting with the tension in the top and at the bottom. So I will say that in a vertical circle, the weight interacts with the tension. Okay, so we do not ignore the weight when dealing with vertical circles. All right, that is the concept for a vertical circle. Now, I will show us a little case study. Let's use an inclined plane. Look at this. Here is an inclined plane. Now, imagine a car or a motorcyclist moving down this plane. All right. Now, if a car is moving down an inclined plane, that car will require little or no effort to move down this plane. But if the car is to climb up this plane, the car will require more force. In fact, the car will have to be on high gear to move up this plane. The same thing happens in a vertical circle. Before the car at the top right here, we require little or no force to turn around this point. All right, so we can refer to this tension here as apparent, because the force at the top here, or the tension at the top here, is very, very small, because the object requires little or no force to move around the top. Now at the bottom right here, just in the same way as in the inclined plane at the bottom, the car will have to require much force to move off this bottom. The car requires what? A much force to move off the bottom of the circle. So what I'm saying is that the tension at the bottom is greater. So the tension at the bottom is greater than the tension at the top. So that is the concept right here. Now, we also have a point right here, a point right here, and a point right here. Now, the points at the sides are also known as our mv squared over r. Okay? But the point at the top and at the bottom, we shall have to derive formulas for the tension at the top and tension at the bottom. But I want us to note that the tension at the bottom is greatest, or is greater than the tension at the top. Now let's look at tension at the top for a vertical circle. So we are considering this part right here at the top. Here's the weight, and we have the tension. Let's call it T subscript T. That's tension at the top. Now we want to derive an equation for tension at the top. Now to do that, we have to find the net force, because both are forces. So we have to find the net force. So therefore the net force is equal to, now because the two forces are going down, because the weight and the tension are moving in the same direction, we have to add. So we add the tension at the top plus the weight, which is Fg. Guys, remember my Fg is the weight, which is equal to mg. Don't forget that. So I'm asked to find the tension at the top. So therefore I will transpose. I will move the plus Fg to my left, becomes a negative. So therefore tension at the top is equal to the net force minus the weight, Fg. Good. So therefore, I can log in my data, and please remember that our net force is equal to mv squared over r. All right? Our net force is equal to mv squared over r. So therefore, I can say that my tension at the top is equal to the net force, which is m, the mass, times the speed squared over r, minus the weight, which is mg. So here is the formula for tension at the top of a vertical circle. As you can see, the net force is, or as you can see right here, we are subtracting the weight from the net force to get our tension at the top. That tells you that it is very minimum. So the tension at the top is always small, or it can be negligible. So we are saying that the tension at the top is just apparent. So here is the formula for finding the tension at the top. So for tension at the bottom, I can draw a sketch of it, which is this. Is a sketch of tension at the bottom. This is our the weight, and here's the tension. Let me call it tension at the bottom. Good job. So to find the tension at the bottom, we have to find the net force, which is net force. Let me use N, ET, is equal to, now because the two forces are moving in opposite direction, we have to subtract. So it will be what? The tension at the bottom minus the weight. Okay, so what next? We have to find the tension at the bottom. So we transpose. I will move my negative Fg to my left, becomes what? A plus. So therefore, the tension at the bottom is equal to net force plus the weight, which is Fg. So therefore, tension at the bottom is equal to, our net force is the same as our centripetal force, which is mv squared over r plus the weight, which is what? mg. So here is the tension at the bottom. As you can see right here, we added the net force to the weight. That tells you that the tension at the bottom is greater or is large than the tension at the what? At the top. So here is how we can derive formulas for tension at the bottom. Okay, so let's look at just a question on how to find the tension at the bottom and the tension at the top. Now, the first thing I do is that I will write out my given data. So I'm giving the mass. The mass is giving us 550. Grams. I have to convert this to kilogram. So to convert to kilogram, I will divide my 550 by 1,000. And that gives us 0.55 kilogram. Okay, so we are given the radius. Radius is 15.0 centimeters. Remember, we have to convert centimeters to meters. To do that, we divide by 100, so 15.0 divide by 100. That gives us 0.15 meters. Okay, we are given the speed. Our speed is giving us 4.25 meters per second. Question says, what will be the tension in the string at the bottom? So my tension at the bottom is not given. And the tension at the top is not given to us. Tension at the top. All right. So I have to find the tension at the bottom and the tension at the top. So I hope you guys remember the formulas. So the first thing I do is this: to find the tension at the bottom, I can draw a sketch. At the bottom is the bottom. This is the weight. And right here is the tension at the bottom, which is acting towards the center. Now, you all know how we derive the equation. So Step 1, we find the net force. So the net force is equal to tension at the bottom minus the weight. So I can transpose, so we have tension at the bottom is equal to the net force plus the weight. And also I know that the net force is equal to mv squared over r plus the weight is mg. Now the reason why I have to derive the equation again is that I want us to note that we don't have to memorize the formula. You can just draw a sketch like this and you should be able to what? To remember the equation from scratch. If you can draw a sketch, you can be able to remember the equation. So what next? We log in data. The mass is 0.55. Times the speed is 4.25 or squared, 4.25 squared over the radius is 0.15 plus mg, the weight, the mass is 0.55 times our g is 9.81. Remember that our g is always constant. It is equal to 9.81. So therefore, I can find the tension at the bottom. You bring out your calculators. 0.55 times 4.25 squared divided by 0.15. That should give us 66.2292. 2292 plus 0.55 times 9.81. That should give us 5.3955. Good. So therefore, the tension at the bottom is equal to 66.2292 plus 5.3955 will give us approximately 71.6 Newton. 71.6 Newton. So here is the tension at the bottom. So to get the tension at the top, if you don't mind, I can draw a sketch at the top. Here's the weight. And here is the tension at the top. So what I do now is that I find the net force. So net force is equal to tension at the top plus the weight, because they are going in the same direction. I add, so I transpose, therefore my tension at the top is equal to the net force minus the weight. All right, so we log in data, or we log in the formulas. The net force is equal to mv squared over r minus the weight is mg. So what next? I log in my data. If you look at the equation, you see that mv squared over r is the same as this. So if you don't mind, I can put in the value, which is 66.2292 minus mg. Our mg is the same as 5.3955 because it's the same value. So it's 5.3955 5.55. So when you subtract 5.3955 from 66.2292, we get approximately 60.8 Newton. So you can see that the tension at the top is less than the tension at the bottom. So that tells us again that the tension at the bottom is always greater than the tension at the top. So here is a practice question for you. Please do this question on your notes. Take a picture of it and send to this email address, and I will give you a feedback if you are correct or not.